Hello, welcome back. So last video we talked about this matrix, the final form of our series of elementary transformations, which gave us this nice matrix with which we were able to find the particular solution, correct? Which kind of came out of this, where we substituted x5 equal to 0, which gave us x3 equal to -1, x4 equal to 1, and then we set x2 equal to 0, and then x1 became 2, and this gave us this particular solution, right? Now, while this is great, next step is for us to go through and write the general solution. And if you remember, we did one example before, so we follow the same approach. So what we do is we look at the columns just like before that don't have this they don't belong to this identity matrix columns, if you want to think of it like this. So here this is 3 by 3, so this column, and this column form the 3 by 3 identity matrix. Then this column 2c2 and c5, if we express these two in terms of the other columns to the left, because you can see the second column is just -2 times this, and then this column is -2 times this column plus this column and -2 times this column, right? So let's write it down. So what is the observation? The observation here is this is if you remember from the one of the previous examples that we discussed before, we obtained the general solution in similar fashion. Let me see if I'm able to pull that particular sheet, and we can go over that quickly. So if you remember, this was the simpler example that we started out with, where we had this identity matrix. Then we wrote this 8,2 for the particular 42,800 as the particular solution, and then we wrote this 8,2 C3 as 8 times C1 plus 2 times C2, and we said this was going to be the 0, right? 8 C1 plus 2 C2 minus 1 C3 plus 0 C4 is 0. Then if you use this, then this is always going to give us 0, because that's the 0 of the matrix, right? Same approach, right? Here column 2 we have to express, so let me write here. So it's column 2, if you see, is simply equal to -2 times column 1, right? This means the whole form is going to have let me write here the general solution. Okay, this is going to be all x in R5, right? This is going to be 5 elements, such that x equals this guy 2 0 minus 1 1 0 plus this is nothing but, so it's minus 2c1, I'm taking it to the left hand side, plus c2, and then everything else is 0 c3 plus 0 c4 plus 0 c5 equal to 0. Why am I writing all this? Because I need all those here, right, for the zeros. So I can then do lambda 1 times minus 2 1, then all those are 0, right? This is the same exercise we did before, right? It's just a little bit, bring it back here. You can see, since this is 0 of a matrix, of this matrix, of then we will work out the math and see that this gives us these don't add anything to the solution, because this is the particular solution. Okay, this is just going to give 0 if we basically this matrix, and then you multiply by any constant times this is going to give us 0, right? And then similarly we write this fifth column C5, this one equals -2 times C1, and then for getting this one we need to add C3, and then to get this -2 again we have to add -2 times C4, right? So then that means essentially take this C5 to the other side, and then I'm flipping the things over, so I'm getting -2C1 plus 0 times C2 plus C3 minus 2C4, and then minus C5 equals 0, right? And these are actually vectors, right? So that means the next one, the lambda 2 term, is going to be plus lambda 2 times this -2, 0, 1, -2, and -1, right, with lambda 1, lambda 2 in R. Okay, so this is the general solution. Okay, so I'm gonna, let me just mark this. So this is the whole thing, right? So this is the general solution. Let me make sure that this matches the book. It doesn't exactly match the book. So in the book they have 2, 0, minus 1, 1, 0. We got that. Plus lambda 1 times. This is given as 2 and 1. Okay, did I make a mistake here? Oh yes, I did make a mistake, because sorry about that. This 2C1 is coming to this side, so this becomes a plus. So sorry about that. So 2C1 plus C2, and then everything else is 0. So this is plus 2, okay, not minus 2. Okay, so that's 2, 1, all zeros. And here also I think this one is all right, except that in the book they are adding, this one is not incorrect, just that this doesn't match the book. In the book they have 2, 0, -1, 2 and 1, and that works because this lambda 2 is any real number, right? So this lambda 2 that I have is just the negative lambda 2 of what is there in the book, and that's all right, okay, because I moved everything, I moved the C5 to the right hand side. Instead, if you moved everything to the left hand side, then you would get, basically you just multiply this whole equation by -1, then you get 2C1, so that gives you plus 2, then this is 0, then this is -1, and this is 2, and this is 1, all right? And again, this is not incorrect, but too many negative signs, so I'll just change it. So I'm just multiplying this whole equation times -1, right? So then this becomes plus, that 0 remains, this becomes -1, and then this is plus 2, and this is plus 1. Okay, hope that was clear. So what we did is we had to get to the general solution after writing this particular solution. So we got the particular solution written down here, and then we went back and we saw which of these columns did not have this kind of, they didn't form the columns of the identity matrix. So those are called the columns corresponding to the free variables, right? So first one is this column C2. C2 is -2 times C1, so we wrote that, and then you move this 2C1 to the left hand side, sorry, -2C1 to the left hand side, that becomes 2C1 plus C2, and then everything else is 0. So that gave us 2, 1, 0, 0. And then here this column 5 is -2 times C1 plus C3, and then this -2 times C4, right? And then you can move this whole thing around, right? And that's how we got this general solution. All right, so I want to still just make sure that it fits, everything fits, right? So let's just verify that it will fit, but we just want to verify, right? So what I'm going to do is not take that original equation, because the original equations that we started with is very complicated. Actually, let me show that to you, where we started with. If you remember, we started with this one. and then that's what we started with. If I have to put that x1, x2, x3, x4 into these equations and verify, it will become very cumbersome, right? But it will work as long as none of the steps in the augmented matrix is incorrect, right? So if we got our augmented matrix correct, then we can just verify in the augmented matrix, which is especially in this nice form, which is known as reduced row echelon form. So we'll talk about that, but let's just, before we move on, let's verify this solution works, right? So I'm going to write this this general solution like before. So the general solution, I'll just write GS. The general solution is of the form x equal to 2, and then in this case it's plus 2 times lambda 1. Okay, I'm going with lambda 1 plus 2 times lambda 2, and then the next entry, so where I got this from is from here, right? So 2, which is the, I'm just writing the top element, 2 plus 2 lambda 1 plus 2 lambda 2, like this I'm writing for everything. The second entry is 0. Okay, second entry is 0 plus lambda 1, and then this is 0, so I write lambda 1. Third entry is negative 1, and then this is 0, and then this is negative lambda 2, this is minus 1, so it's minus 1 minus lambda 2. And then this one is 1, this is 0, 1 plus 2 lambda 2. And then the last one is, this is 0, this is 0, this is lambda 2. Okay, so lambda 2. This is the general solution. Okay, we just wrote it in that this form. I just took it and added them all up, right? Check, right? So we are going to verify if this kind of x1, x2, x3, x4, x5 work with these equations, right? So we have to check whether, so I'm just going to rewrite these equations in the other page so we can verify. So this is going to be x1 minus 2x2 minus 2x5 equal to 2. So is this correct for this, right? So if we take this is 2 plus, okay, so let me write it down. So x1 is 2 plus 2 lambda 1 plus 2 lambda 2 minus 2 times x2, which is minus 2 lambda 1, minus 2 times x5 is lambda 2. That's the left hand side, and then you can see these guys cancel, right? So all of them cancel out, so this is good. So we got 2, so this works. Let's check. And this x3 plus x5, is this equal to negative 1? What is x3? This guy, minus 1 minus lambda 2, and this is x5 plus lambda 2. Okay, so this also works because these two cancel, so this works. And then x4 minus 2x5, is this equal to 1, right? x4 is 1 plus 2 lambda 2, and minus 2 times x5 is minus 2 lambda 2, so that also works. So all those three works, right? So this general form basically fits into that solution fits into these equations. So this was our set of equations, right? And in these equations, this solution fits, so everything works. Okay, so awesome. That was a long example. It took multiple videos. Hopefully the steps were clear, and I tend to err on the side of verbosity and boredom, maybe over skipping things and you getting confused. So that's why I go through some of these laboriously. Hopefully it's clearer this way, right? Okay, so now finally I get to chance to go back and read from the book again. So on my copy, this one, the general solution for this problem is equation 2.47 or 2.47. Let's read further, right? In fact, in the book, they have written this particular solution and they have given the general solution just like that, right, without stating all the steps, and they are explaining that afterwards. So let's go through that. So they are saying in the following we'll detail a constructive way to obtain a particular and general solution of a system of linear equations, which is exactly what we did, right? Now the pivots and staircase structure. So they have this pivots and staircase structure, right? What is this pivot? The leading coefficient of a row, first non-zero number from the left, is called the pivot, right? So we have to go back to our example in this augmented matrix, right? The leading coefficient of a row, right, which will correspond, for example, in this case the leading coefficient is this, or maybe a different, let's take even this matrix, right? In this matrix, this is the leading coefficient, -2, so this is called the pivot, right? And is always strictly to the right of the pivot of the row above it. So in this case, again, they won't call it pivot because they are talking about this whole thing only with respect to row echelon matrices, okay, not with respect to general matrix. So my bad for thinking that this matrix could be taken as an example. So let's not take that matrix as an example. Let me take my row echelon form if I can find it. We did talk about this row echelon form before we went into this reduced row echelon form. So this was the matrix. So in this row echelon form, the leading coefficient of a row, the first non-zero number from the left, which is this guy and not this one, and then this row, this is the guy, and then this one, this is the guy, right? So those three are what are known as pivots, and is strictly to the right of the pivot of the row above it, right? So all these pivots are to the right of the rows above it, right? Therefore any equation system in row echelon form always has a staircase structure. So what is the meaning of staircase? So they are drawing something like, if you think like you can draw like this, right? So it is a staircase where you are climbing from like this, right? You are climbing from the bottom right to the top left. That's what they are saying as a staircase structure. Okay. So a matrix is in row echelon form. All right. So let's look at the definition. It is in row echelon form if all rows that contain only zeros, like this one, maybe even sometimes this could also be zero, when that it's a useless equation in that case. But all rows that contain only zeros are at the bottom of the matrix. Correspondingly, all rows that contain at least one non-zero element are on top of rows that contain only zeros. Okay. Looking at, so that's the first one. The second condition is looking at non-zero rows only, like for example like these. The first non-zero number from the left, right? So any first non-zero from the left, so you go traverse like this, right? Also called the pivot or the leading coefficient, is always strictly to the right of the pivot of the row above it, right? So we saw that too, right? So in this case, this pivot is to the right of the row above it, and this pivot is to the right of the pivot above row above it, pivot of the row above it, right? So that's good. Then there is a remark about basic and free variables. The variables corresponding to the pivots in the row echelon form are called the basic variables. So these x1, in this example, x1, x3, x4 are the basic variables, and the other variables, which is x2 and x5, are free variables. Okay. So in this example, which is example 2, let me make sure I got this right. So this is example 2.6, right? Example 2.6, and the equation in the book that they are talking about is 2.45. These equations in the book is 2.45. Okay, so that's all these equations together. So for this row echelon form, the basic variables are x1, x3 and x4, and the free variables are x2 and x5. Okay, and then they are going about explaining how to get this particular solution, right? So row echelon form makes our lives easier when we need to determine a particular solution. To do this, we express the right hand side of the equation system using the pivot columns. Okay, so this guy using the pivot columns, right? So that's what they are doing, such that b equal to summation of lambda I pi, where pi are the pivot columns. So actually that's another thing, we maybe don't need the for the pivot column. So let's see what that is. So they are saying you can just do it like this, okay, which is you try to express this is directly, so we did it from the reduced row echelon form, which was much easier, but they are explaining how to do the particular solution from the row echelon form itself. Okay, so let's see what they are talking about. Okay, so they are saying b, the right hand side, if you remember, right? So what is the right hand side here? B is this one, right? This column vector is b. Okay, b equal to summation of I equal to 1 to uppercase P lambda I, this P I, right? Okay, so P I is the pivot column, right? These are the pivot columns, Pi. So I equal to 1 to P, which is there are capital uppercase P pivot columns, and you take lambda I times Pi. So what does that mean? That means they are saying express this B, right, as the linear combinations or combinations of this and this column, right? So let's see if we can do that. And then they don't worry about this a plus 1. Okay, so because it's all 0, they're setting it at to 0. We don't need to worry about that. We just need to only take these three and then see if we can get this. So how can we get this? Let's see, to first write the equation here. Okay, so I'm going to take lambda 1 times 1 0 0, that's the first pivot column, plus lambda 2 times this guy 1 1 0, right? 1 1 0, plus lambda 3 times negative 1 1 1. Okay, this should be equal to 0, right? 0 minus 2 and 1. I mean, in general you will have fourth one, but since these are all zeros, we don't need to worry about that case. Okay, so they are saying you solve this, then you get some lambda 1 lambda 2 lambda 3, and then from there let us see how to get the particular solution. Okay, it's a little bit tedious. If you have the reduced row echelon form like we had before in the previous video, it's easier, right? But let's go through the steps, right? So how can we do? So basically we have to now write three equations, right? The good thing is this lambda 3 is 1, right? Because, okay, let me write down this equation. Three equations we can write from this. So this is going to be lambda 1 plus lambda 2 minus lambda 3 equals 0. That's the top one. The middle one is, this guy is gone, lambda 2 minus lambda 3 equals minus 2. Okay, then these two are gone for the bottom equation. Lambda 1 times 0, lambda 2 times 0 are 0. Then lambda 3 is 1. Okay, so since lambda 3 is 1, let's substitute back into this. So we get lambda 2 minus 1 equal to minus 2. So lambda 2 becomes minus 1. And this means lambda 2 minus 1 for lambda 2, sorry, lambda 1, then minus 1 minus lambda 3. So that's this minus 1 equal to 0. So we get lambda 3 equal to 1, lambda 2 is minus 1, lambda 1 equal to 2, right? Lambda 1 equal to 2 from here, right? When we put everything together, we must not forget the non-pivot columns for which we set the coefficients implicitly to 0, right? Therefore, we get the particular solution 2, 0. Okay, so they have taken this, if you see this becomes 2. But we have to be careful here, right? Because this 1, 2, 3, this 1, 2 and 3 are not x1, x2, x3, right? They correspond to the basic variables, which is x1, x3 and x4, right? So this guy, okay, it is a little bit confusing how to do this. So that 1, 2, 3 correspond to the pivot columns, but the pivot columns are not x1, x2, x3. The pivot columns are x1, x3 and x4. Okay, so the x2 and x5 are 0. Okay, so that's how they are getting the particular solution, where this 2 fine, because that is the first column. So that is what we took here, 1, 0, 0. So that's fine. So we can use the 2, right? But you remember the second column is a corresponds to a free variable, so that's 0. We have to set that to 0. And then the lambda 2 corresponds to x3, so we have to write the minus 1 there. And then the lambda 4 corresponds to the x4 corresponds to lambda 3, so that's 1, and then we get 0, right? So this is 2, 0 minus 1, 1, 0. So this is the same thing, even though this is quite a bit of little bit more work than what we got with our like this reduced row echelon form. Was much easier to work with. Okay, this is the where we made sure that everything else is 0. Otherwise you are still going and you are solving these equations here like this, right, with the row echelon form. Okay, so that's not too bad, just more tedious, I think. Okay, so the reduced row echelon form, now they are introducing reduced row echelon form, right? So row echelon form, right, we saw already the definition. For row echelon form, the leading entries, the pivots need not be 1, right? They can be any non-zero, right? But I don't know whether row echelon form itself is used by itself. The reduced row echelon form is what is nice and easy to solve and easy to work with and probably more useful. So let's focus on what is the reduced REF is for reduced row echelon form. Okay, so first one thing is it is in row echelon form, so it must be a row echelon. The matrix must be in row echelon form. Second one, every pivot is 1. Okay, which means in the general row echelon form case, pivot need not be 1. So pivot is 1 for reduced row echelon form. Then the third one is more important. The pivot is the only non-zero entry in its column. Now that's what we got here. You remember this matrix, pivots are all 1, and then that's the one. Remember this is the REF. This is the REF. This is the reduced REF. Okay, so hope that's clear, because the pivots are all 1, and then no other entry in the column, pivot columns, that's the only non-zero entry, and it is 1. Okay, so that's what this reduced row echelon form is. Okay, and this is very important. Reduced row echelon form, or it's also known as row reduced echelon form, it's another way, or it's also called row canonical form. Okay, and all right, so that's the reduced row echelon form, or RREF. Okay, the reduced row echelon form will play an important role later in section 2.3.3 because it allows us to determine the general solution of a system of linear equations in a straightforward way. And then the remark is Gaussian elimination is an algorithm that performs elementary transformations to bring a system of linear equations into reduced row echelon form. Okay, so we'll do one more example and then we'll close. So this example is 2.7 in the book, and this is the reduced row echelon form. Okay, here they have given the matrix, this matrix A, which is like this: 1 0 0 3 0 0 0 1 0 0 0 1 and 3 9 negative 4. Okay, they are giving this matrix A, and they have bolded this, but I'm just going to circle them. So this is the one pivot, here is pivot, and here is pivot, and this is in row reduced echelon form because we can see it is in row echelon form because obviously the staircase thing holds, right? And then it is also in reduced row echelon form because the pivot is 1, and in every column, pivot column, only the pivot is 1 and everything else is 0. Okay, so the key idea for finding the solutions of Ax equal to 0 is to look at the non-pivot columns, which we'll need to express as a combination of the pivot columns, right? So we see that the second column, basically to the left, you will see, because of the staircase nature, any non-pivot column you can always express as a linear combination. Means you just do some scalar multiplication to the columns on the left, the pivot columns on the left, and then add them up, right? So in this case, 3 times C1 equal to the C2 is 3 times C1, right? And then these two are pivots, so no problem. This guy is 3 times C1 plus 9 times C3 minus 4 times C4, right? So to obtain a 0, all we need to do is just this, right? So the general solution, so basically now they are taking Ax equal to 0, right? So they're not worried about Ax equal to B. Let's just take Ax equal to 0. So the general solution will be of the form, in this case, x belongs to R5, such that, because the particular solution is 0, so you don't write it, such that x equal to, you take lambda 1, right? And then you know C2, so let me write that down, C2 equal to 3 times C1, so 3C1 minus C2, right? And then everything else is 0, so 3C1 minus C2, I'm not going to write 0 C3, essentially is plus 0 C3 plus 0 C4 plus 0 C5 equal to 0. Okay, that's what this is. So we can simply write it as 3 minus 1 0 0 0, right? So that's that. Plus, what about lambda 2? We take this fifth column, C5, and write it like this: C5 equal to 3 times C1, right, for the 3, and then this 9 is plus 9 times C3, and then this guy is minus 4 times C4, right? And then you take the other side, C5, and then this is nothing but 3 times C1, and then 0, and then this guy is 9 times C3, and then this is negative 4, right? And then this goes that side, so that becomes negative 1, right? With lambda 1, lambda 2 in R. So this is the general solution for Ax equal to 0. Hopefully that was clear, and I'll see you in the next video.